so this is the second to last lesson in chapter 4. So by now, chapter 4 is like almost done. You should really get some like serious progress on chapter 4 ALEKS this weekend. So rational functions and inequalities. So a rational function is a function that can be written in the form f of x is p of x over q of x. And the kicker here is that p and q are polynomials. So all the stuff that we're doing today applies because these functions are polynomials. They're not polynomials, sort of different things can happen. So something like x squared plus 1 over 2x plus 3, that's a rational function. Would x squared plus 1 over root x plus 3, would that be a rational function? No, because technically root x plus 3 is not a polynomial. Does that make sense? Okay. So the first thing we're going to do with rational functions is find their domains and find their x-intercepts. Okay, so what might be problematic with a rational function? We already did this, right? Where the denominator equals 0. So take that function, factor the denominator if it factors. Does x squared minus 11x plus 30 factor? How? X minus 5, x minus 6. So for the domain, x cannot equal 5 and 6. Let's also give that as an interval. So what, negative infinity to 5. Union
5 to
6. And just so it's clear, you do use parentheses there, because if you use square brackets, you've actually included that number, and you don't want to include it, you want to exclude it. Okay, how about the x-intercepts? So for the x-intercept, what do you set to 0? The whole thing, you set the y equal to 0. If you cross the x-axis, you have to have an x value that's non-zero. Well, I mean, you could be 0, but usually isn't. So 0 equals x minus 4 over stuff. How might you start solving that equation? Multiply by the denominator. What does multiplying 0 by that denominator do to the denominator? It makes it go away, right? It's kind of nice. You get 0 equals x minus 4. And so at what x value does your graph cross the x-axis? At x equals 4. Technically, it's the point 4, 0. But that's the point where you hit the x-axis. The next one is very, very, very similar. How about you give it a try while I have a sip of coffee? Does anybody dare to tell me what numbers you got for your domain that x couldn't be?
Negative 3 and 1.
Okay, x cannot equal negative 3, 1. As an interval, that's negative infinity to negative 3. Union negative 3 to 1. Union 1 to infinity. Is that okay? All right, x-intercepts. set y to 0. You didn't have to factor that numerator right away, but I just chose to. And then you're going to get 0 equals 3 times x squared minus 4 over your denominator. But what happens to your denominator? Poof, it goes away. So you have 0 equals 3 times, how does x squared minus 4 factor?
X plus 2, x minus 2.
Very good. So this graph has two x-intercepts, one when x is positive 2, one when x is negative 2, right? So there are two separate ordered pairs, negative 2, 0, and 2, 0. So that graph crosses the x-axis twice. Does that make sense? Okay. All right. Now, this is just an aside to the next question. When you graph a rational function, they sometimes, not always, but they often have things that are called vertical asymptotes and horizontal asymptotes. So a vertical, what that will look like is this, is there's these lines. And your function might look something like this when you look at its picture. And those lines that kind of fence it in, they're called asymptotes. This one's called a horizontal asymptote. Asymptote. And this one's called a vertical. And they're called that because they're horizontal lines and vertical lines. Does that idea make sense? Now, rational functions specifically don't cross their asymptotes. If a function has a vertical asymptote, the function never crosses that. But there are functions that are not rational functions that have horizontal asymptotes that they cross an infinite number of times. Like here's an example of something where that would occur. You can have these functions that are infinite oscillators, where they oscillate, but their oscillations get smaller and smaller and smaller. And technically, this line is an asymptote because as you get further and further out to infinity, the function kind of shrinks down to that line. But the asymptotes we're going to discuss for this lesson are the ones where the rational function won't cross it. And there's actually a really easy pattern within the equation so you can figure out what those are, okay? So that's what the next slide says. It's huge, so bear with me. So a vertical line, x equals a, is a vertical asymptote if your function either goes to infinity or negative infinity. This notation means you approach a from the right. That means you approach a from the left. So write that little bit down so you know what that little notation means. Like squeeze that in there. And we'll draw a little picture and show you what I mean by that. I'm going to usually draw my asymptotes as dotted lines. So what they mean is as you get close to that number, your function either gets really, really, really big or it gets really, 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 really negative. That's what it means to be a vertical asymptote. Does that idea make sense? Okay. And actually, the way to find vertical asymptotes is said below. So if you have a rational function, the first thing I want you to do is factor the numerator and denominator. So that's your first step. You always take the function and factor the numerator and denominator if they do factor. Okay. If you have a number that's a 0 of q of x, that's the thing in the bottom, and also a 0 of p of x, then the graph has something that's called a hole at this point. What this will correspond to in your simplifying is you will have factors that cancel. And we'll graph things that have holes and we'll discuss them. Okay, so, but this basic idea is that if something's a 0 at the top and the bottom or some factors cancel, that problem kind of goes away and it's a hole. It's the little problem as opposed to an asymptote is kind of a big problem. And if you have a 0 of the denominator that's not a 0 of the numerator, then the graph has a vertical asymptote. This will be the factors that don't cancel. So those are vertical asymptotes. And I think this will make a little bit more sense when we have examples, but that's the general statement.
So both the numerator and the denominator factors that you get, the ones that are left after canceling, those are vertical asymptotes?
Let me do an example and then we'll see if you're right, okay? And the last thing is horizontal asymptotes. So horizontal asymptotes are horizontal lines, right? If you think about a picture, that's kind of like the end behavior of the graph. Does that make sense? Like what happens as you go to the right, correct? And what happens as you go to the left. And so going to the right means your x is going to positive infinity, right? Does that idea make sense? Going to the left, what does that mean x is doing? X is going to negative infinity, exactly. And so when you have a rational function like this, if your m is less than n, so m is the power in the numerator, so power in numerator, then y equals 0, or the x-axis is a horizontal asymptote. This would be something like x plus 1 over x squared plus 1, for example, okay? That would be an example of this. The power in the top, or the degree, is smaller than the power in the bottom. And when you plug in huge numbers, who's bigger, the numerator or denominator?
Denominator.
And it's a lot bigger. Does that make sense? If you plug in a million squared is a lot bigger than a million. Does that idea make sense? So you'll have a number divided by a number that's much larger, that's going to go to 0. If those powers are equal, say something like 2x squared plus 1 over 3x squared plus 7, for example. If you plug a number in, and like a huge number in and square it, add 1, does adding 1 really change that number at all? Not so much, right? Plug a number in, huge, square it, multiply by 3 to add 7. Does the add 7 do much? No, so this is really kind of like 2x squared over 3x squared, which then reduces to 2/3. Oh, you stupid pencil. Okay, and then the last one that kind of got a little bit cut off on my slide is that if m is bigger than n, there's no horizontal asymptote. So what that's saying is if I have a numerator where the power is bigger than the denominator, then you have a big number divided by a not as big number, which is going to be infinity of some sorts. So let's apply those to some specific examples. I think it'll make a little bit more sense. You've got to be a little bit careful when you write your answers for this. So writing a vertical asymptote, make sure you call it a line x equals because it's a vertical line. Horizontals are y equals, okay? Okay, so vertical asymptote, those are the easiest one. Is there any factoring necessary we have to do here? No, because we have just like a thing. So vertical asymptotes are going to occur where the denominator is 0 after you've factored and canceled. So we're looking for where does 4x plus 2 equal 0? That's the place the vertical asymptote occurs. 4x equals negative 2, right? So x equals, no, negative 1/2.
Oh, yeah.
And you can think, okay, well that's the number that x cannot be, right? And so that means that the graph will not cross that line. Okay, so that's the vertical asymptote. Now the horizontal asymptote that's what happens as you plug in huge numbers for x. If you have 9 divided by 4 times a humongous number, like say 1 million, what is 9 divided by 4 million and 2? approximately.
Zero.
It's pretty darn close to 0, isn't it? Does that make sense? So the horizontal asymptote here is y equals 0. And how that relates to the rules you were given on the previous page is that the degree of the numerator is 0, because it just has a constant. The denominator's degree is 1, it's bigger. But you can think, okay, 4 over huge number makes 0. Horizontal asymptote is the same thing as end behavior. Just we didn't talk about end behavior with rational functions yet. Yes?
So you're saying that this isn't the actual, very precise horizontal asymptote, it's more of an estimation?
So it is the exact horizontal asymptote, but what happens to your function is it approaches it but does not get all the way to it. I think that's what you're thinking. So what this would look like as a picture
Yeah, I think.
is you'd have a vertical asymptote at x equals -1/2. And as you, I think it would look like this. It would go down to the y-axis on that side, and it's going to go up to the y-axis on this side. And we will actually talk about how to graph them specifically, but to do that we have to know how to find these asymptotes. Okay, how about this next one? So let's say VA for vertical asymptotes, and write that whole thing every single time. So does the numerator factor and simplify?
No.
Not so much, right? So vertical asymptotes happen where the denominator is 0 after cancellations. So when does x minus 3 equal 0? X equals 3. So that's your vertical asymptote. Now the horizontal asymptote is what happens as x goes to positive and negative infinity, and with rational functions it will do the same thing at those values. Pretty sure. Yes, okay. So now this one, think plugging in humongous numbers. You do humongous number times 6 minus 11 divided by humongous number minus 3. Isn't that going to be like about equal to really 6x over x? For really, really big numbers. So that will equal 6. So think as I plug in big numbers, my result, my answer gets close to 6. And if you want to convince yourself to take a calculator and plug in even like 100 or 1,000, you're going to get numbers that get closer and closer to 6, the larger and larger they get. So that's the line you're approaching as you plug in larger and larger numbers. What happens in the end is you go to 6. Yeah, do you have any questions or are you stretching?
Both.
Okay.
So 6, because 6x and x will have the same,
Uh-huh.
or
The same power degree,
the
yep.
m and- yeah.
The m and n are the same, exactly, yep.
Then you just divide.
And another way to,
Have the variable in front.
yeah, another way to think about these horizontal asymptotes is that the biggest power is actually all that matters ever. So what you can just do is you can always look at the largest power over the largest power. And if you have 6x over x, then that cancels to 6. And if you would have had 6x squared minus 11 over x minus 3, you would have had 6x squared over x, just taking the highest powers, which would give you 6x. And as x gets large, this thing still goes to infinity, meaning there's no horizontal asymptote. And if I'd reversed it and I'd made it like, let's say 6x minus 11 over x squared minus 3, the most important powers are the biggest ones. And if you simplify 6x over x squared, you get 6 over x, right? And as you plug in large x's, this 6 over x is going to go to 0. So another way to think about it is just take, okay, the highest powers are the most important ones, everything else you disregard. And that's because as you plug in super large numbers, those other numbers added on don't affect it very much. Okay, how about this one? So I don't know if that numerator factors.
Doesn't, I would divide by -2.
I think it actually might though. Like,
I would divide by -2 first.
I would take out the -2 in the numerator, which is kind of what you're saying. -2 positive x squared minus 3x plus 2. Does that make sense to everybody else? So does that actually factor technically?
Yes.
I think it does. But when it factors, is it going to cancel with the denominator?
No.
No. Okay, so in that case, it's actually a little bit less important, but it is important to always check, because if something cancels, a little bit different thing will happen. Okay. So vertical asymptote. So that's going to happen when what is 0? When 2x minus 5 is equal to 0. So that means 2x equals 5, right? At x equals 5 halves or 2.5, you have a vertical asymptote. For the HA, let's use the idea that all that matters are the highest powers. So who is the most influential player in the numerator?
X squared.
Technically, it's negative 2x squared. The coefficient comes with it too, just in case, okay? Who's the most important thing in the denominator? 2x. And that simplifies down to negative x, yep. So does it make sense here that as x goes to infinity, this f of x, or the y, is going to go to negative infinity then? Because you think, okay, well, plugging numbers into that thing is the same as plugging numbers into this thing for really, really big numbers. And so if we plug in big numbers, you're going to have big number made negative, right? And then as x goes to negative infinity, where is this picture going to go? It's going to go to positive infinity. And so this is, when that happens, there's no horizontal asymptotes. Some math people refer to that as your function blowing up, as in getting large is blowing up. They have to be careful to do that in airports.
Yeah,
Don't talk about things blowing up in airports.
Do you have a story behind that, or?
I think that somebody might have been, like some math geeks might have been talking about something where the terms were like suspicious sounding. And I don't know if it was specifically blowing up, but I think that it actually happened to somebody. Because we're geeks, we don't think about it that way, right? We just, anyway, okay. So that one, and also as that relates to the stuff that was on the previous page, you see how the power is higher on the top than the bottom? And when that occurs, there'll be no vertical asymptote. Okay?
If we got like a number, like if we got 2 left over, that would be the asymptote.
Exactly.
If the variable in there, it's no.
Exactly. If the variable's in the numerator, if you're left with an x, then there'll be no asymptote. If you're left with like a 1 over x, then it would be 0, because 1 divided by a big number makes 0. Okay, yeah.
Is that the notation that you want us to write down?
I just care that you can figure it out. These, really, if you know your patterns well enough, you can figure it out just by looking at the equation. Does that make sense? So I want you to be able to look at it and figure it out. That's just me writing some work down so you can hopefully understand what's going on. I don't care if you write that work on your quiz.
So there's no actual like horizontal asymptote.
This one wouldn't have a horizontal asymptote. Like if you were to graph this function, it'll do some weird stuff in the middle, but it's going to go down forever and ever in that way, and it'll go up forever and ever in that way. That's what that like thing says. And if you want to confirm to yourself what's going on, you could use a graphing app, and you could look at these pictures and see, okay, as I plug in bigger x's, does my thing approach a line of y equals whatever? Okay, vertical asymptotes. Does x squared plus 4 ever equal 0 for real numbers?
No.
No. So this does not happen. There are none. If that denominator had been x squared minus 4, would the answer have been different? Yes. Okay. Now the horizontal asymptote. So think, what happens when you plug in humongous either positive or negative numbers? You get 3 divided by some number squared, right? Plus 4. So 3 divided by a big number will make 0. Does that make sense? Okay, so the horizontal asymptote in this case is y equals 0. And what you should be able to do is look and say, oh, the denominator has a much larger degree than the numerator, and therefore the denominator is going to dominate and it will go to 0. Okay, so So let's actually do some graphing now. So we're going to graph these rational functions. And so I actually took these questions from like sample questions from ALEKS. This is how they're going to require you to do it as well. So what you need to do is you need to draw in the horizontal and vertical asymptotes, and you need to plot 2 points on each piece of the graph. What they mean by that is that the vertical asymptote divides the graph in half. And you've got to plot 2 points on the left of it and 2 points on the right of it. Okay? So first step is to find the vertical asymptote and find the horizontal asymptote. So the VA is, the HA is. So what is the vertical asymptote in this particular case? X equals 4. Does that make sense? Okay. How about the horizontal asymptote? Y is 0, yep. And I'm not sure how ALEKS will have you plot those, but I'm just going to draw them in as dotted lines. So there's x equals 4, and y equals 0 is the x-axis. If on your quiz you don't draw in the x-axis as an asymptote, I'm not going to dock you for it because like it's already sort of bolded and it's hard to see that you've drawn it in. Now the second thing is pick points. And I'm going to make 2 tables. You could make this as 1 table if you want to. It just helps me to think about it as 2 separate pieces. So you've got to pick one side where your numbers are on the left side of your vertical asymptote, and some numbers where your numbers are on the right of the vertical asymptote. So let's do the left side first, and pick easy ones. Don't pick like negative 100, that's silly. 1, yeah, 1's an easy one. 0 is an even easier one, does that make sense? So if I plug in 0, the y is negative 4 over 4, or negative 1. Does that make sense? And so that point plots from the origin. You go over nothing, and you go down 1. I would suggest trying to pick numbers that work out nicely. So while plugging in 1 is pretty easy, you end up with negative 4 over 3, which is a fraction, and I just don't want to deal with fractions. Does that make sense? So how about we plug in 2? If you plug in 2, you get negative 4 over what? 2, which equals negative 2. So over 2, down 2, and that's this point right there. Did I count right? And so what you know now is your picture on this part's going to probably look like this. It's going to just go to its asymptotes. If you wanted to verify, you could pick another number, like you could pick, I think 3 works out pretty well. If you plug in 3, you get negative 4, I believe. Does that make sense? So over 3, down 4. See, that's that point right there. You kind of get the idea that as you approach that vertical asymptote from this side, your function is decreasing forever and ever. Now next, pick some points on the right of negative 4. So what's a good, you can't pick 4 itself, right? Because 4 will make the denominator 0. 5, yeah, 5's a good number. Plug in 5. So x is 5, y is negative 4 divided by what? Negative 1, so that will be positive 4. So over 5, up 4. Does 6 work out okay?
Yes.
I think it does, yep. So 6, we have negative 4 over negative 2, which is 2. Over 6, up 2. And you see you're looking about like this. Yes?
So isn't this just, it's not really the origin, but it's symmetrical to the...
It has odd symmetry about the line x equals 4. Yep.
Okay, so
Yeah.
once you
All
find one side, you can just
You can kind of reflect and get the other side for certain kinds of functions because it does change depending upon if you have a squared or like an odd or even power. So until you are 100% certain that the pattern is there, I would definitely just plug in numbers and check. But there often is some symmetry, and you can use it to check and see if your answer is correct. Do you see what he was saying? Okay. It's not that hard, is it? It's just a little bit tedious. Okay, so for this one, where is the vertical asymptote? And where is the horizontal asymptote? 0 again. Okay, so use that information. How about you try to graph that a little bit and just see if you can get the right numbers coming out and figure out what to plug in, because that's the trickiest part. Sorry, it went a little bit off my grid. But did you get your picture looking approximately like that? Did anybody plug in numbers other than 0 and 5 on the left?
I plugged in 12 just because it looks nice.
You plugged in 12?
Mhm.
Holy moly, 12's way off the end.
Yeah.
And that also isn't on the left of 6.
Plugged in
3 worked out well, yep. That would be 6 over -3, which is -2.
I did 3 and 5.
Okay. All right. But you got the same conclusion for about where the picture was lying, right? And as long as you give ALEKS 2 correct points on either side, it doesn't matter which 2 points those are. Does that make sense? Okay. So now let's do a few that have horizontal asymptote that is not 0. Okay, so I'll do part A and then we'll have you do part B and I'll check it. So for this one, where's the vertical asymptote? X equals -3, very good. Okay, how about the horizontal one here? Nope. 2. The numerator being 0, I think that's what you were thinking of, that isn't a horizontal asymptote. That just tells you where it crosses the x-axis. For the horizontal asymptote, it's where you look at the highest powers only. Okay, it's all good. That's what learning's all about. It just happens. Okay. And I'll make the tables, or table, plug in numbers on either side, and try to find ones that work out nicely. I'm pretty sure that, because these questions came from ALEKS, and I clicked it repeated times to see if it would give me like similar combinations, and they seem to all have numbers that worked out nicely. So what's a good number to plug in on the left of this x equals -3 line? -4 might work out well, don't you think? So if you plug -4 in, the numerator is -8 plus 3. The denominator is -4 plus 3. If you make any mistake in these things, it's going to be a sign error when you're doing your simplifying, because it's just like you just do it dumb. And your picture looks all wacky. So if I do -8 plus 3, I get -5, right? And if I do -4 plus 3, I get -1, yes? So that will equal 5. So back 4, up 5. There's that point right there. I don't think plugging in -5 works out well. Not super well anyway, you get like a fraction. Does that make sense? So let's try -6. So did -6 work? I think it did actually. So when you plug -6 in, what do you get in your numerator? -12 plus 3, great. Divided by -6 plus 3, right? So that's -9 over -3, which will give you 3. So back 6, up 3. On the right, I'm plugging in 0. You plug in 0, you get out 1. Okay. It probably is easier if you plug in numbers that are like a little bit closer to that vertical asymptote. Does that idea make sense? So I don't think -1 works out very nicely. I actually plugged in -2. When you do that, you get -4 plus 3 over -2 plus 3, which will be what? I think it's -1 over 1, yep. So go back 2 from the origin, down 1. And there's your picture. Okay, try part B. It's pretty similar. Just give it a shot. Find the VA, find the HA. Did you get it, Tristan?
Yeah, sorry, that's.
It's okay. still working is totally fine. Just have more coffee. I think that the hardest thing with these problems is just the fact that you've got to play around a little bit with which numbers to plug in. Does that make sense? Technically, anything is good except for 3 in this case. Does that make sense as well? But I'm not sure how much tolerance ALEKS has for you plotting numbers that are not whole numbers on a graph. Does that make sense? Yeah.
It's full tolerance of that. You can, as long as you plot the point, like type in the fraction.
You type in the fraction? Okay, so in that case, it's totally fine. Yeah, that's good to know. But it is also nice to have whole number points, isn't it? But in case you can't find one, and just use the fraction, it's not a big deal.
You can also type in decimals as long as they're not repeating.
Exactly, which you could then give as fractions instead, and then they're all of a sudden they're exact. But the basic idea is that when you have to graph a function, find the important features, and for rational functions, the important features are the asymptotes, and then plot some points. Does that idea make sense? Okay. How is example 6 a little bit more complicated than the previous ones? It doesn't have a horizontal asymptote. Does that make sense? Okay. So that's one difference with it. Find the vertical asymptote and plot that. Okay, we'll have a VA at x equals 3. This function will have something called a slant asymptote that we're not going to discuss yet. But slant asymptotes are things where they're slanted lines and your function approaches that slanted line as x gets large. Okay, so we'll talk about those on Monday, but this has that, but we're not going to discuss it. Not yet, anyway. Okay, so a VA at x equals 3, and there is no HA. And the reason there's no horizontal asymptote is because the numerator's power is bigger than the denominator's, right? Okay, and so then just pick some numbers on either side of 3. So I can tell you what I chose. I did succeed at finding numbers that worked out well. So when I plugged in 1, that worked out all right. So that's going to give me 1 minus 6 plus 1. Over 1 minus 3. So the numerator there will be -4. The denominator would be, so overall that'd be 2. 1 up 2. Plugging in 0 doesn't work out super nice in this case, does it? So I was like, oh, I'll try -1 then. When you square -1, what happens? Positive 1. Does it make sense that I would then get plus 6 plus 1? Okay. Over -1 minus 3. So that's 8 over -4 or -2.
I would have plugged in 2 instead.
Oh, it's totally up to you. And so this function's going to do something like this. It'll keep going down forever and ever. Because it doesn't have any kind of horizontal asymptote. Now let's pick some other numbers on the other side. So what, you can't pick 3. How about 4? 4 would be okay, right? One way you can tell a number is going to work out nicely is that, like, say when you plug in 4, your denominator is 4 minus 3, which is 1, and dividing by 1 will always yield a whole number. Does that make sense? Okay. So this will be 16 minus, what's 4 times 6? 24. Great. Plus 1, all over 1. Oh, so arithmetic. 16 minus 24 is -8, plus 1 is -7. So over 4, down 7. Okay. Plugging in 5 also works out well. So that's 25 minus 30 plus 1 over 5 minus 3. So that numerator is 6, is that correct? And what's the denominator? Over 2, does that make sense? Did I do that right?
-6. Wait.
Is it?
No, -5.
It's not even -6, it's -4, isn't it? Yeah, I'm so sorry. That was your awake test, guys. I think you passed. -4 over 2, which is -2. So over 5, down 2. And it just goes up forever and ever. Yes,
So we're gonna have to find the line.
we will do that on Monday.
Okay.
So on Monday, we'll talk about when you have these slanted asymptotes and how you find them. You actually use long division. So it's not that bad. It's actually kind of cool. It's kind of cool that they approach a line as opposed to just go up and grow. So, I mean, it's a different kind of asymptote, and it doesn't come up all the time, but it's good that you see it in case you get taught it in calculus. Then you'll know it and you'll be like rock stars.
Actually, I'll just wait till Monday.
Yeah, wait till Monday. Yep. Okay, now the next thing and the last thing we'll discuss today is what happens if your fractions cancel. Okay, so like what does the picture do in that case? So this one is doctored to work out well for you. So take the numerator, factor it. What do you get? X plus 5, x minus 5. And the denominator, take out the greatest common factor, and you have 5x plus 5. And notice how that simplifies to x minus 5 over 5, right? When that happens, x equals -5 is going to be a hole in your graph, not an asymptote. Asymptotes are problems that don't cancel. This problem cancels, it's a little problem. So it's fixable. And if you even told like a computer to graph this function, it won't recognize that there's a hole there. Like it won't find it. So here's what we should do. Let's draw in a vertical line at x equals -5, even though we're not going to have an asymptote there. I'm just going to write a note to myself saying that I know my function will have a hole there. Does it make sense why you can't plug -5 into the original function? And even though you cancel and simplify, you have to retain the fact that you can't plug -5 and that has to stay. So now the question is how might you graph this? And we'll see if you guys can one-up my Algebra 2 students from high school. Without even plugging stuff in. That's a 1 in front of that x. Both pieces are divided by 5, right? 1 over 5x minus, exactly. Do you guys see what he did there? Divided both pieces by 5, right? And so now it's a line, y equals mx plus b, right? So where does this line begin? -1. And you rise 1, you run 5. Or you go down 1 and backwards 5, and as you cross that dotted line, you have to leave a hole. So this is a line with a little hole in it. That's something called a removable discontinuity because you can fix it by just filling the hole in. If you were to graph this thing on like a graphing app or on something online or even a graphing calculator, I don't think the calculator will recognize that there's a hole there. It won't plot that for you. It's not that smart. But it will tell you that you get this kind of line shape. Does that idea make sense? Okay? All right. So how about the next one? So factor the numerator. 3 parenthesis x minus 4. How about the denominator? X minus 4, x minus 1. And so how does that simplify down? 3 over x minus 1, right? So at x equals 4, you have what? There's just going to be a hole there, right? As in just a missing value. at x equals 1, what do you have? That one didn't cancel, did it? So if it doesn't cancel, that's the vertical asymptote. So let's draw in lines at 1 and at 4. And let's just put VA under that one, hole under that one, so you know what's going to happen when you draw your picture. Okay, and now you just plot this 3 over x minus 1 function, just like we did in the previous thing. What's this horizontal asymptote? Y equals 0 is the HA, so you've got, the x-axis. So pick some numbers to the right and left. Now, which number, you pick things to the right and left of the vertical asymptote in this case. Does that make sense? So pick numbers on the right and left of 1. So a good number to plug in would be -2. Sure, I was going to plug in 0 first because I like 0. So when you plug in 0, you get -3. -2 is also a great number. You plug in -2, you have 3 over -3, which is -1, right? So plot those 2 points. So over nothing, down 3, back 2, down 1. So there you go. And that's a filled in dot, just in case that wasn't clear. Now pick some numbers on the other side. What's one number that will work out pretty well? 2. So that will be 3 over 1, I believe, right? So 3 over 2 up 3. 4 would work out nicely if we could plug it in, but here's what you can do. You can plug it in,
We could put a,
and you can put a circle, an open circle there. You'd have 3 over 3, which is 1. But technically, you can't plug in 4, so you have to just put an open circle where that number would be if you could plug it in. And so there's your picture. And I think the nice thing about putting the vertical line in where your hole is that you know when you cross it, that's where to leave an open circle. Does that idea make sense? Okay. And if you actually, you can plug that number into the simplified form, right? You just can't plug it into the original. And when that happens, you can put the value at what you get when you plug it in the simplified form, but you must leave an open circle there. And a lot of the stuff you'll do in calculus early on talks about limits, and you talk about how to fill in that hole correctly. I think I have one more. Yep, okay. So these examples, there were these questions, and I looked through ALEKS, because I tried very hard to make sure I went over everything that was like the stuff you're going to be asked. There were these questions that were matching, and they said match the function with its graph. And what you need to do is use some of the stuff you know to figure out what the, say, vertical asymptotes would be, what the horizontal asymptotes would be, and then if you can figure out if function's even or odd, you can pretty much guess which one is right. Does that idea make sense? So for this one, I think a good place to start if you're given a rational function and asked to figure out what its graph is find the asymptotes. So for this one, what are going to be the horizontal asymptotes? What are going to be the vertical asymptotes? So what's the HA? Y equals 0. So every graph that didn't have that as an option, you cross that off and don't guess that, right? This guy will have vertical asymptotes if x squared minus 9 equals 0, right? How many vertical asymptotes will it have? 2. So they will be at x equals what numbers?
3 and -3.
3 and -3. Okay. So you look at the choices and you say, okay, well, all the functions that don't have those vertical asymptotes in that HA are not my guesses, right? Now the rest of it you can figure out using even or odd. So remember that to check for even and oddness, what do you plug in for x? No, you plug in negative x. So that will be 3 times negative x over parenthesis negative x squared minus 9, right? What does that give you? What's the numerator?
-3.
And the denominator is x squared minus 9, right? Is that the original function? No, so it's not even. Is it the original function multiplied by -1?
Yes.
It actually is. If you take this thing, and you can see how this is tricky, if you multiply this by -1, that's multiplying by -1 over 1. So only the numerator or denominator will change, not both. So this is actually an odd function. So what kind of symmetry should the picture that you're looking for have? Like if you had a picture, you had two choices. One looked like, I don't know, this, for example. And one looked like, these are totally guesses, okay, so don't quote me if these are right. One looked like that. Which one has the right symmetry to be an odd function? The bottom one does. Does that make sense? Okay, I think we can do the last one, because it won't be very long. So if you're already ahead and you got this, find the VAs and HAs. Just give it a shot. It won't hurt you to try. Give it the good old college try. You're right. Okay. So this one, what's the vertical asymptote, or totes? X equals plus or minus 1, very good. This one has an HA at y equals 2. And so use that to eliminate some of the guesses, and then check for evenness, oddness. Well, hello, train. I wonder if the train gets recorded in the video. Does it? Kind of fun. Okay, so when you plug in negative x, what happens? Nothing, as in your function goes back to exactly what it was, right? So this function is even, and the picture you're looking for will have symmetry over what? Over the y-axis. So by now,